Okay, good morning. Let's continue. So yesterday we were talking about inferential statistics, right? In other words, to make guesses about certain features of a population based on sample information or sample statistics, right? Sample mean, sample standard deviation, you name it, right? Any kinds of descriptive statistics, we can use that to make inferences about the population. Um, so we said that as a brief review, right? Oops, sorry. There are two types of statistical inferences that we can make. The first type is called point estimate, right? Point estimate. That means we're making a single guess, right, about a particular feature of a population. Say we're interested in guessing the mean, right, of the population, right? Mean attitude, average attitude of the population on a certain issue that we're interested in. So we say that based on the sample from the population, we calculate a mean to be 4. And so we guess that, okay, so based on this one single, point value, we say that, well, that's pretty much our only guess, right? That's the only information we have. So we say, well, then the population mean, right, will be about 4. Okay. Similarly, right, if we're talking about proportions, presidential race or any kind of election, right? Say we say, well, the mean proportion for a particular candidate is, 60, I don't know, 65%. Okay. And again, you are drawing a subset of individuals from a population that you intend to study, and therefore this by no means is the complete or true information, right? But again, you guess, okay, so given this is my only piece of information, or the only piece of information that's available to me, I'm going to make a guess, right? So in the population, if everybody on that particular day turns out to vote, then I will guess the candidate will receive a similar amount of support. That's around 65%. Okay, so that's make point estimation. But as we just said, right? So point estimation, though, even though it's sample mean is a good estimator of population mean, and sample proportion is good estimator of population proportion. But that does not mean that these estimates or these estimations are 100% correct, right? There will always be errors, right? Due to sampling, the random, due to random sampling, due to any other kinds of random forces, right? A particular individual change his or her mind, right? That could certainly happen. So in other words, we are always not certain whether these will be exactly the population mean or population proportion. So that's why we introduce a second type of estimation, and that's interval estimation, right? Interval estimation. With interval estimation, we are calculating a certain interval, right, with a lower bound and upper bound. We said that, okay, so we are making a point estimation saying that the population mean will be 4. But just to be certain, or just to be sure that, we allow a certain amount of fluctuation, right? We allow a certain amount of wiggle room, so to speak, right? So that we say that there's a chance that the actual population mean or actual population proportion will fluctuate from value A to value B through this particular point estimation. It could be 4, but it could be, let's say this is 3 and this is 5, right? It could be 4, it could be 3.3, it could be 4.7, right? So any value in this interval will be possible, but will provide one value that's most likely, right? and that's 4, the point estimate. Okay. Well, I shouldn't say most likely, but that's a value that is to be expected, right? Other values are equally likely, but this is one sort of typical value we use to provide a concrete piece of information. Okay, so that's the usefulness of interval estimation, right? It actually gives you a wider, a more information, right? More pieces of information than a point estimate. It tells you the range of possibilities, right? Actually, that's better, right? Than a single number. Okay, so that here's where we ended yesterday. Um, we actually can read these kinds of sentences in newspapers or in scientific journals saying that we're X% confident that the population mean or population proportion will fall within the range of da da da. Okay, so the question is, of course, where does this 95% come from, and how do we generate this interval? Do we just make it up? Okay, well, of course not, right? So today, I'm going to teach you how to generate this interval, right? And we do have a name for it, right? We call this, this interval that we generate confidence interval, or CI for short. Okay, so this CI will tells you the following information. That is, at a certain probability level, right? 80% or 95% or 99% or any percentage you would like, right? So given that means, if you repeat, many times, like 1,000 times, or 100 times, just to make things simpler, right? So if let's say, okay, let me read through this, definition before I sort of dissect this sentence for you. Okay, so CI, or confidence interval, it tells you that at a certain probability level, that your interval based on the sample data, right, the sample that you actually collected, will include the population mean or proportion or correlation or mean differences, whatever, right? That means, whatever feature that you're interested in about the population, right, will be included in the interval that you generate. Okay, so okay, now let's look at this sentence more closely. What it actually means is this. So this certain level of probability, let's say, for now, let's just randomly assign a value to it. And let's say that, this interval, let's make something up to make it 3 and 5, right? Just to stick to the example that we just used. And the population means 4, okay? So this is the mean that we try to guess, right? So based on the sample, because we can easily calculate the sample mean, we can sort of make a guess that, well, given that sample mean is a good estimation of population mean, we can say the population mean is probably 4, okay? But here's the question that your boss or, other people, your reader, your audience might ask you. What do you mean by probably? Well, how probable, right? So here is, this probability comes in useful. So when we say that we're 90% confidence, or with a probability of 90.9, then my interval 3, 5, right? This is our sort of a hypothetical interval. My interval 3, 5, that is calculated based on our sample, which I'll tell you how to do in a minute, will include the population mean 4, which is based on our guess from the sample mean. Okay, so the process is like this. We collect a sample, we calculate the mean, and we say this, well, we calculate the mean to be, sample mean to be 4. Because the sample mean has been proven to be a good estimator of the population mean, so we'll make a first guess, saying that because the sample mean is 4, I guess that the population mean is also 4, and it's likely, well, probably to be 4. Okay, And now the question becomes, how do we quantify this probably being 4, right? Probably being 4. Okay, so can we describe it, right? Can we describe the sentence that's based on probability? So based on certain procedures, we can generate a confidence interval, let's say it's 3 and 5. And we say that we're 90% confidence, or there's a probability of 0.9 that this confidence interval should include the true population mean, 4. So again, right, it doesn't have to be 4, right? We're making a point guess that's 4, but by calculating a confidence interval, we're saying that it could be 4, it could be 3.2, it could be 4.8. As long as this value is larger than 3 and smaller than 5, we're good, right? We'll have a good enough guess. So that means, and now let's understand this probability. So this probability means if we, right? So here we're drawing only one sample, okay? But the problem is by drawing a different sample, you're very likely going to obtain a different mean, right? So let's say this is the sample mean of the second sample. And because you're likely drawing in different groups of individuals, there should be some kind of difference between this mean and the first sample mean, right? So it could be 3.8, okay? And you keep on drawing more samples, and this time you have a sample mean of 5.2, and you draw 100 samples so that you have 100 sample mean. And the last sample 100 mean will be, let's say 6.3. Okay. Now, this 90 percent probability will say that once you draw 100 samples, then it must be the case, and it's very, very likely to be the case, that some sample mean would fall in this interval, whereas others, like this one, will fall above, and this one as well, right? Will fall above or fall beyond this interval. But how many sample means will fall in this interval, and how many will fall beyond this interval? Well, about 90, right? Because we're saying the probability is 90, right? So we're saying given 100 samples, then 90 sample means will fall in this interval, whereas because of a randomness, there will be about 10 sample means that will fall beyond, greater than 5 or smaller than 3. Okay, so that's what this sentence means, right? That's to tell you that, in other words, this interval 3 and 5, 90% of the time would include the true population mean, right? The probability that we're interested in guessing. And this interval, about 10% of the time would not include the sample mean. So that's why we're saying that we're 90% confidence that we will have a population mean that's included in 3 to 5. Exactly what it is, we don't actually know. But statisticians and many, pollsters actually are satisfied with this interval because, as we'll see in a minute, right? Sometimes this interval, despite seemingly being sort of rough and approximate, actually can tell you a lot about the population probability that you're interested in. Okay, but anyway, this is what this sentence means, right? It means 90% of the time, this interval will include a value that's the true population mean or proportion, and about 10% of the time, this interval would not include the population mean or population proportion. Okay? Okay. But how do we calculate, what's going on here? How do we calculate this interval, right? So previously, we're making sort of we're making up things, right? We say that, well, we randomly assign a number 90% as our confidence level, and we make up interval 3 to 5, right, as an example. But in reality, of course, we can't just make up stuff. There's a formula, in fact, to help us calculate the confidence interval. Okay, so the confidence interval, to calculate that, we need first of all the point estimate. We also need z-score and something that we'll call standard error. So before we understand what standard error is, I will first of all draw your attention to this formula. This formula is actually not new. Okay, we have seen actually something that's very similar to this formula not long ago, and I would like to ask you what it is. Okay, what is the formula that we previously talked about and spent quite much time practicing it that actually resembles this formula? Okay. Well, you saw z here. That should ring a bell. What is the formula for z-scores? Z-score, as we said, is a particular value, right, minus the sample mean divided by standard deviation. Do you see the similarity here? Okay, so first of all, you say, well, okay, so I see a z here. There's a z here, but here is z multiplied by something, but I don't have a multiplier of z here. Well, that's easy, right? We can simply move standard deviation to here, and it will become a multiplier of z. Okay, so we can transform this formula to z times standard deviation equals to x minus sample mean. Okay, you would say, well, wait a minute. Where's this guy? Well, if we move, actually, right, this mean to the other side of the formula, we'll have m equals to x minus z times standard deviation. How about that? Now this will very much look like this formula. Because wait a minute, interval ci is an interval, whereas sample mean is only a value. Interval is a range of value. This is only one single value. That's fundamentally different. Well, congratulations, you're noticing the key difference here, but it's very easy to actually generate an interval from this formula. So here we only have x minus z times standard deviation. But what if we also add, right, a second formula that's x plus z times standard deviation? That will give us a second mean or second value, right? Now we have essentially a lower bound and an upper bound. So these two means actually will give us the confidence interval. So confidence interval, as now we see, is intricately associated with the z value. It's essentially, right, we're converting the z formula to the formula for confidence interval. Now we say, wait a minute, Andrew. Here, okay, so it appears that this formula, is it's the same for the formula for z, but we have standard error here, SE, but not standard deviation, right? That seems like another difference. Well, you're right. But it turns out standard error is just a special type of standard deviation, right? So later on, we'll tell you how to calculate standard error based on standard deviation, but for now, you just need to remember that, in fact, standard error is just a type of standard deviation. Now, right, we have exactly, you know, we have a lower bound for the mean, and we have an upper bound for the mean based on the formula for z. Okay, and this x, remember x, when we discuss the formula for z, is a particular value from the sample, which is exactly a point estimate, right? So imagine that from the sample we don't know, imagine we put all these values into a jar and we just stick our hand into the jar and randomly pull out a number. That will be our point estimate, actually, right? That will be our point estimate of the average value for this particular sample, right? So this is essentially our point estimate. Okay, so now you should see that this formula for confidence interval is actually an old friend, right? We have seen it before. Okay, nothing too mysterious about it. So then, what is confidence? Okay, so now let's understand this concept step by step. So imagine, right, we sort of conducted a survey, which includes this 7-point scale of opinion on gun control to a sample of Honolulu citizens. And we assume that, to simplify the example, the scores, right, by these sample of Honolulu citizens are normally distributed. And we'll calculate the population mean, or actually we don't need to say that this is a population mean. Sample mean will be good enough. Okay, sample mean. So then we'll calculate the mean for the sample to be 4 and the sample standard deviation, right, to be 0.05. Okay, so this is our sort of example. Now, given this distribution, the sample mean is 4, right? And the sample distribution is, I believe, 0.5. Okay. Now, given this distribution, right? Given we say that the distribution is normally distributed, the data are normally distributed, has a mean of 4 and standard deviation of 0.5. Now, let me ask you, if I randomly draw a value from the sample, what is the likelihood that this value to be greater than 3.5 and smaller than 4.5? Okay. Again, my question is, given this distribution is a normal distribution, it has a mean of 4 and a standard deviation of 0.5. Then if I randomly draw one and only one score from the population, from the sample, what is the likelihood that this value is greater than 3.5 and smaller than 4.5? That is, will fall in this interval. That actually becomes the question of using the empirical rule, isn't it? The content that we discussed yesterday or the day before, right? So the empirical rule says 68% of the scores from a normal distribution will fall within one standard deviation above and below the mean. Okay, and it turns out if we do a simple calculation, right? So 3.5 is the x here, right? Is the x here equals to 3.5. Then let me ask you, what's the z-score associated with 3.5 in this distribution. Easy, right? We use 3.5 to minus 4, and we divide it by 0.5. That will give us the z-score for 3.5, and it is exactly -1, right? So this 3.5 minus 4, that's -5, negative 0.5, and negative 0.5 divided by negative 0.5, that's exactly -1. Similarly, right, the z-score for 4.5 will be equal to 4.5 minus 4 divided by 0.5. 4.5, sorry, 4.5 minus 4, that's 0.5. 0.5 divided by 0.5, that's 1. There we go. It turns out that 3.5 and 4.5 are exactly 1 standard deviation below and above the mean. And we know from the empirical rule that the probability is 68%, right? 68% of the time, or the scores from this normal distribution will fall in 1 standard deviation above and below the mean, in this case, between 3.5 and 4.5. Okay? All right? This is the conclusion that we just drew. And therefore, in other words, right, we're 68% confidence, right? We're confident at a 68% level that any individual score will be between 3.5 and 4.5. This makes sense because we know that, if there, 100 scores, right? If there are 100, exactly 100 scores, from the empirical rule, we know that 68 of them, right, out of the 100 scores, 68 of them will be greater than 3.5 and smaller than 4.5. Then it makes perfect sense for us to use this percentage, right, 68 divided by 100, right, percentage, to describe our confidence level. Because in this case, right, there will be no more, no less, but exactly 60 of the 100 scores that will fall between 3.5 and 4.5. So that's why we say that we're confident at this particular level that any individual score will be between 3.5 and 4.5, and therefore, right, the 68% confidence interval, or CI, will be 3.5 and 4.5. You see the connection here between z-score and confidence interval? Okay, let's look at another example. So given the same distribution, right, it's a normal distribution, the mean is 4, the standard deviation is 0.5. Okay, then what's the likelihood that a single individual score is between 3 and 5? Well, easy, right? First of all, we'll calculate the z-score for 3. So 3 divided minus 4 divided by 0.5, that's -2, right? So that's a -1 divided by 0.5, that's -2. And we have 5 minus 4 divided by 0.5, that's 1 divided by 0.5, so that's 2. Aha! We know from the empirical rule, right, the 95% of scores from a normal distribution will fall within 2 standard deviation below and 2 standard deviation above the mean. Okay? And therefore, we're confident at a 95% level that any individual will have a score between 3 and 5. And that's why the confidence interval here will be 3 and 5. Okay? So now we should see, right, that this confidence level has a lot to do with the z-score, right? If the z-score is 2, then according to the empirical rule, we have a confidence interval, a confidence level of 95%. if the z-score is 1, according to the empirical rule, we have a confidence level of 68%, right? So that suggests actually the confidence, right? What we call confidence in the context of inferential statistics, essentially the probability associated with z-values. Okay, so if we have a z-value of 1.28, the confidence level will be 80%. If our z value is 1.65, right, our confidence level is 90%. And if our z-score is 2, right, well, more precisely, it's 1.96, right, but roughly we say it's 2, the confidence level is 95%. And if our z-value is approximately 3, well, to be exact, it will be 2.58. But the empirical rule is sort of an approximation, right? So we say that when z-value is 3, then the confidence level is 99%. Okay, that is, we're almost certain we're almost certain that all values from the population, from the sample, sorry, will be within 3 standard deviation above and below the mean, right? So given this, formula, right? So CI equals to sample mean. Now we're talking sample mean as the point estimate here, plus and minus z timed standard error, right? Or standard deviation, right? Doesn't matter. So let's say, given this, formula, you want to be confident at an 80%. Okay, you don't need to be very confident here. It happens when, for example, you're given the first trial to answer the question, right? You want to sort of explore all the possibility here. You don't, and the result is not that important. So it's okay, right, to assign a low probability to it. So then you will use accordingly a z-value of 0.8, right? But if this result is very important, you want to be more confident with your estimation, then you will choose a higher probability level. Then you will use z equal to 2, right? And this is indeed the most commonly used confidence level. Okay, so that's how we sort of will choose confidence levels and the z. Okay, so now given this formula, now we have the z-score, right? Z-score we can choose from this table. So that's one known value here. So what we don't know then will be what is the sample mean, or what is the feature point estimate, right? We're trying to make inferences about, and what is the standard error here, or standard deviation. So these will be the two unknown values we need to calculate from the sample. Once we, from the sample, calculate the mean and calculate the standard deviation, and then we can choose according to our needs the z-value that we need, and then we can easily calculate the confidence interval. Okay, so now I will be teaching you how to obtain these two values with concrete problems. So let's start with sample proportions, because that's actually more close. Well, I shouldn't say more, but very closely related to our real life, right? Because, for example, we say that there will be about 65% people supporting a certain presidential candidates, right? So let's denote the sample proportion as P, right? That's our observation. Right? We observe from a sample that 45, I don't know, right? 65 or any kind of percentage of people from the sample will support certain candidates, and we surveyed N people. Okay, so the 95% confidence interval, well, we're using 95 because this is the most commonly used confidence interval, right? So the 95% confidence interval will be the sample proportion minus or plus the z-score associated with the probability of 0.95, which is 2, right? We just said that, times this whole thing, which will be our standard error for proportion. Because the general formula for confidence interval is point estimation, or let's use x, right? The point estimation could be sample mean, could be sample proportion, plus or minus z, right? Whose value is to be chosen, times the standard deviation or standard error of the point estimate. Because now we're talking about proportion, right? So we, replace p here for x, and then we need a formula to calculate the standard deviation for proportion, sample proportion. It turns out that this is how we calculate standard deviation for sample proportion. It will p multiplied by 1 minus p divided by sample size, and we take the square root. Okay? So, right, so this expression is exactly the standard error or margin of error, right? That's exactly the sort of question I asked you at the start of yesterday's class, right? What does it mean to say that the survey has a X% of margin of error, right? Margin of error is essentially the standard error for the estimated proportions. Okay, so now we can sort of start to answer a more concrete question. For example, your boss asked you, well, from a sample of 500 Honolulu citizens, 60% of them favor gun control, right? Well, we know that we can sort of make a guess based on the sample proportion. Then we can say, well, then for the entire population of Honolulu citizens, then approximately 60%, again, probably 60% of all Honolulu citizens will also favor gun control. But then we can't be certain, right? We only said that probably, based on sample information, that 60% of all Honolulu citizens are favoring gun control. But how do we quantify this probably, right? Well, we said that we're going to use confidence intervals. So the boss will ask you, well, then give me an interval estimation, right? How likely this population proportion are going to fluctuate, right? So what's the range, in other words, of fluctuation of your guess? It could be 60. I know it's a good guess, but what's the extent? What is the extent to which that the true proportion, right? The proportion from the population will fluctuate around 60%, right? Okay, so what do we do? All right, easy. This is our question, and this is our formula, right? And then we know that P is 0.54. That's from the question. And is 500, and we know that from the table that we in the previous slides, right? The Z score for 90 for the probability level of 95% is 2. So this guy here, the standard error or margin of error for this particular sample proportion will be, what is it? Okay, it will be 0.54 times 1 minus 0.54 divided by the sample size, which is 500. Okay, so we can calculate this together. It will be 0.54 times 0.46, right? It will be, if I'm doing this correctly, 0.2484 divided by 500. Okay, divided by divided by 500. And we take the square root of that value, right? Don't forget about that step. It will be, I think, point 0.02. Okay? And then we ask ourselves, what is the 95% confidence interval, right? Given this finding here. So, whoops, right? We're doing this correctly. So the standard deviation, this guy here, is 0.022. Well, 0.02, close enough. So now we can write out the whole thing, right? It will be 0.54 plus or minus. We know z 95% is 2, right? 2 times 0.02. So you'll be 0.54 times plus or minus 0.04. So it will be interval 0.50 or 0.58. Boom. That's our 95% confidence interval for this sample proportion. That means, sure, we can make a single point estimation saying that based on the sample, there will be about 54% of all Honolulu citizens, right? Not just 500, because we're extrapolating this information to the entire population. So we can say that about 0.54% of all Honolulu citizens will be favoring gun control, but this percentage, the true percentage, might fluctuate around this percentage from 0.50 to 0.58. And we're 95% confident that the true proportion, the true population proportion, will be within this interval. That means, if we draw 100 samples from the population, there will be exactly 95 samples that will yield a proportion that's between 0.5 and 0.58. Sorry, 0.50 and 0.58. There will be about 5 samples that will yield a proportion that's either smaller than 0.5 or larger than 0.58. 0.50 or 0.58. Okay, so again, right, this is the meaning of 95% confidence interval. So if this is our 95% confidence interval, it means if we draw 100 samples from the population, right, all Honolulu citizens, there will be exactly 95 samples that will yield the proportion, which would not be exactly 5.4. It could be, doesn't have to be, but the sample proportions from these 95 samples will be greater than 0.50, smaller than 0.58, and there will be about 5 of them that will yield proportions that's beyond this interval. And that's why we said we're not 100% confident that, this interval will include the population proportion, right? We're given some, a room for possible errors, but in most cases, 95% confidence level is good enough. Okay. Okay, so this, to be exact, right? If we use 0.022, right, the confidence level will become 0.496 to 0.584. Okay, so this is sort of approximation, but this will be the exact confidence levels. Okay, so of course, right, the confidence level will change each time you draw a new sample, because we know from the formula, right? Formula Ci equals to, well, we're using proportion here. So, right, so Z 95% SE, right? So we know that the confidence interval for sample proportions will equal to the sample proportion minus or plus the z of a certain confidence level timed or multiplied by the standard error of the sample proportion, right? So we know that this guy, sample standard deviation or standard error of the sample proportion equals to p times 1 minus p divided by n, right? So that means if we know sample proportion, then we know its standard error. But of course, each time you draw a new sample, right, this p will likely to be different. It could be the same, but likely it will be different, right? So because the confidence interval, in other words, will depend on the proportion, right? Um, we have, we can now interpret the meaning of this, 95% confidence interval, right? This is exactly what we said before, right? This confidence level will change depending on p, and that's why, from the another way to understand it is because each time we'll have a new confidence, right? New confidence interval. Then these, if we draw a sample, if we draw 100 samples, that means we'll have 100 confidence intervals, right? And then this 100 confidence intervals, from these 100 confidence intervals, 95 of them would include the population proportion, right? And about 5 of them would not include the true or the population proportion, the proportion to be estimated. Okay, and only about 5 of them would not include the true population proportion. Okay, so that's another way to understand this 95% confidence interval. Okay. Okay, so here is the confidence interval that we just calculated from this question, right? So let's to be exact here is from 0.496 to 0.584. That means the population or true proportion of support gun control will be any value between the lower bound and upper bound. Okay, it will be some value, right, between these two within this interval. Okay, so now my question is, if this is our confidence interval, 195% confidence interval, right? And if the meaning of it is that the true proportion of support gun control is any value or any value between these two values, can we say that the majority of Honolulu citizens will favor gun control at a 95% confidence interval? Can we say that? Can we say that we'll have a clear majority here? You say, wait a minute, we should have a clear majority here because, hey, we have a sample proportion of 54%. But wait a minute, this is just one sample, right? We're saying here, if we draw more samples, let's say 100 samples, 59 of them will range, the proportion from 95 samples will range from 0.496 to 0.584, right? In other words, there will be a range of variation here. That means it's not, it could be 54% exactly, but it doesn't have to be. Right? It could be any value, right? The proportion, the population proportion. We're not talking about, right, the sample here. We're talking about the population proportion here. So the question is, well, if this is the proportion interval, confidence interval for population proportion, that means any population proportion could be, anywhere between these two values, then can we say that the majority of Honolulu citizens will favor gun control at a 95% confidence interval? Okay, well, you should pause here to think about it for a while before listening to my explanation. The answer is no, right? And the reason to say no is because this confidence interval includes 50% or includes 0.5, right? 0.5 is the split or the threshold for majority, right? If you have exactly 50% of Honolulu citizens support gun control, that means you will have another half of the population that is against gun control. Then you don't have a clear majority. Even worse, if the true population proportion is not even 0.5, right? Because it could be any value that's greater than this, smaller than this. It could the true population proportion could be 0.497. And if that's the case, this is actually a minority, right? By no means this will be the majority. Okay? And that's why we should say no, because exactly the interval includes 0.5, right? So in other words, the sample proportion, uh, 0.54 is not meaningfully different from zero point 0.5 at a 95% level, right? There's a difference. Of course, these two values are different, but statistically they're the same because this difference of about 0.04 could just because of chance, right? Um, these two values are not, meaningfully different because the interval that we calculated, the 95% confidence interval that we calculated for this point estimation includes 0.50, and therefore these two values are not meaningfully different. In fact, right, if this is the confidence interval for this sample proportion, that means 0.54 would not be meaningfully different from any values that fall in this interval, including 0.50. Okay? All right, so now let's repeat this exercise from a sample of 500 Honolulu citizens. 56%, 56 now it's not 54, but 56% of this 500 people favor gun control. Now, what is the 95% confidence interval of the sample proportion? Okay, so we can do the calculation together. So CI will be equal to, right, the point estimation for proportion plus or minus the z value for 95% confidence interval times its standard deviation, standard error. Okay, so this is our formula here, and we know that proportion, the p here is what? P here is 0.56, and we know that this guy, or the z value for 95% confidence interval, would be 2, right? Now, our only problem is to solve standard error for proportion, and we know the formula, right? So this will be 0.56 plus minus 2 times 0.56 times 1 minus 0.56 divided by sample size is 500. Okay? And this will equal to 0.56 plus minus 2 minus times. So if we do the calculation for this, square root thing here, right? So it will be, let me do this together. Or let us do this together. So it will be 0.56 times 1 minus 0.56. It will be 0.44, I believe. Okay. That will be 0.2464 divided by 500. which is a very small value, but don't forget to take the square root of it. So it will be about if I did this correctly, it will be again 0.022, right? So it will be 0.56 plus minus 0.044. Okay, so 0.044 plus 0.56 will be, so the interval will be 0.64. Right, this is 0.56 plus 0.044. That will give us 0.604. But then what is 0.56 minus 0.044? That will be, we have 0.516. So this should be our confidence interval. Let's check. Exactly, right? So the standard error is still 0.022, but now because we have a different proportion here, so the confidence proportion will also be different. So this time it's 0.516 to 0.64. Now let me ask you, if this is the confidence interval for the sample proportion here, can we say that the majority of the Honolulu population will favor gun control? Is there a majority? Is there a majority now? The answer should be yes. Now there is a majority. That's because despite the fluctuation around 0.56 from 0.516 to 0.64, all possible values, right, at the 95% confidence interval will be greater than 0.50, right? It will be greater than half, right? The smallest value here is 0.516, which is still greater than 0.05. That means even if we take this value as our smallest possible sample proportion, right, because of fluctuation, right, it will still be a clear majority, right? Not by a huge margin, but still is a clear majority. So that means, right, statistically speaking, this value, 0.56, will be significantly different or meaningfully different from 0.50 at 95% level. Actually, all values within this confidence level, because this interval does not include 0.50, all values within this confidence level interval will be meaningfully different from 0.50. Okay, so that means the majority of Honolulu citizens favor gun control because the smallest possible value, the smallest possible population proportion is a clear majority. So we're pretty sure, right? Or 95% confident that the majority of Honolulu citizens favor gun control. Okay. Okay, so that's how we calculate 95% confidence intervals for sample proportion, and how do we use this sample proportion to make to draw very useful conclusions. Okay, so tomorrow we'll be talking about how do we calculate the 95% confidence interval for sample mean, which will be very similar given this general formula here. Okay, I will see you tomorrow then.